This is Topic 1, Math Skills, Section 1.3b, the rules for determining significant figures. Now, in the last video, we learned why significant figures are important. In this video, we'll be learning how to determine, when looking at a number, how many of the digits are significant. Our first step is to distinguish zeros from non-zeros, and it's very straightforward. Zeros are sometimes significant and sometimes not significant. I'll be showing you later how to figure out when a zero is significant and when it's not. Non-zeros are always significant. Non-zeros would include 1, 2, 3, 4, 5, you know this, 6, 7, 8, and 9. These are non-zeros. Now, a zero with a dash on top, a dash or a line on top, or a dash or a line on the bottom is known as a dashed zero, and they are also always significant. Dashed zeros we will put in the category with non-zeros. I'm going to speak very briefly about the special case where there is a zero with a dash or a line either over or under the zero. Now, your teacher might not teach this particular designation for significant figures. If you don't need to know it, then maybe you might want to skip this part. But if you do need to know it, here we go. Now, this only applies when there is no decimal. So here we go. When there is no decimal, and some of the zeros are significant, and some of them are not significant, we must use a dash or a line, whatever you want to call it, either over or under the last significant zero. Some people put the dash over the zero, some people put the dash under the zero. It doesn't really matter. Either way, for this number here, the only number that is significant is the 2. This number has one significant figure. If there is a line over a zero, then that zero becomes significant. This particular number has two significant figures. If the line was here, remember we said over or under, so what the heck, let's just put it down here. Now you have three significant figures, 1, 2, 3. Now if all four numbers were significant, then there would have to be a decimal point here. All right, so again, here we have 1, 2, 3, 4 significant figures. Now, I will be going into these rules in much more detail. All right, right now, I just want you to notice that sometimes there is a zero with a dash over it or under it. You should consider a dashed zero to be the same as a non-zero. Follow all of the rules for non-zeros if you see a dashed zero, like this one or this one. All right, so again, just quickly here with the dashed zeros. Here we have a dashed zero, which is significant, and therefore 1, 2, 3, we have 4 significant figures here. 4 sig figs. All right, now here, the same number, but the dashed zero is over here. Now we have 1, 2, 3, 4, 5, 6 significant figures. All right, so for the rest of this video, we want to look at the rules for significant figures, and you want to learn how to look at a number and decide how many of the figures, how many of the numbers in that number are significant. Because different teachers and professors all over the world use different systems for numbering the rules for significant figures, I think I'm going to resist the urge to number the rules. Let's just say I'm going to teach you 5, 6, maybe 7 rules for determining significant figures, and you'll find that my rules are the same rules as the rules that any teacher or professor will be teaching you. They might just be worded a little bit differently. We're going to quickly take a look at the rules for determining significant figures, and then I'll show you how to use the rules with some real examples. Now, you're going to want to memorize these rules. And the best way to actually use them is to kind of quietly say each rule to yourself very quickly as you judge for a particular number whether the figures in that number are significant or not. Now, let's look at the rules. Non-zeros. Now, if your teacher mentions the dashed zeros, leave these words "and dashed zeros" in the rule. If your teacher doesn't care about the dashed zeros, then you really could just erase the part that says "and dashed zeros." All right? Unless you'd like to know it for your own knowledge, so that when you get into college, you already know it. All right? Now, non-zeros and dashed zeros are significant, always. Zeros that are between non-zeros and dashed zeros are significant, always. Zeros that come before, the word before, very important, before the first non-zero are not significant. Remember, I'm going to be showing you how all these rules are used and what they mean in just a minute. Zeros that come after the last non-zero are significant only if there is a decimal point. So what that means, for example, zeros after the last non-zero. Well, this is the only non-zero, so it's the last non-zero. The zeros after the last non-zero would only be significant if there was a decimal point. So this number here, the 2, is significant. Those zeros are not significant. Now, this is the same number, 2,000, but there is a decimal point. So that's when this comes into play here. Zeros after the last non-zero, this 2 is the first and last non-zero, it's the only one, and because there is a decimal point, all of these zeros now become significant. Again, zeros that are after the last non-zero are significant if there's a decimal point. Well, there's a decimal point, so all these zeros are significant. All right, notice again that the presence of a decimal point changes these 3 zeros from not significant to significant. That's what this last rule here is telling us. Let's take a quick look at one short example. Here we have one significant figure. And remember, I'm going to go into much more detail in a few minutes. Now here, because we have a dashed zero, we have 2 significant figures. 2 sig figs. And here, because there's a decimal here, we have 1, 2, 3 significant figures. 3 sig figs. Now, this is the number 300 with 1 significant figure. This is the number 300, the same number, with 2 significant figures. And this is the number 300 with 3 significant figures. Remember, as we learned in the previous video, and you can go back to that video if you'd like to, what this means is that a very inexpensive piece of equipment measured this number, a very expensive, very accurate piece of equipment measured this number. The best way to apply the rules and really learn how to do it quickly and easily on your own is to say each rule quietly to yourself as you circle each significant figure in red. So here we go. Non-zeros are significant. Non-zero, non-zero. So here we have 2 significant figures. Put the 2 in the box if you are using the worksheet. Here we go. Non-zeros are significant. Zeros between non-zeros are significant. Zeros before the first non-zero, there are none. All right, here's the first non-zero. There are no zeros before the first non-zero. Zeros after the last non-zero. All right, let's say this is I'll put a little F for first non-zero. This is the last non-zero. Zeros after the last non-zero are significant if there's a decimal point. There's no decimal point. This 0 is not significant. So here you have 3 significant figures. Go through the rules again. Non-zeros are significant. Zeros between non-zeros are significant. There are none. Zeros before the first non-zero, F. Here's the first non-zero. Zeros before the first non-zero are not significant. These zeros are not significant. So this number has 1, 2, 3 significant figures. Again, put the number of significant figures into the box if you're using the accompanying worksheet. All right. Non-zeros are significant. Zeros between non-zeros are significant. Zeros before the first non-zero, there are none. Zeros after the last non-zero, zeros after the last non-zero are significant if there's a decimal point. There's a decimal point, therefore those two zeros are significant. This number has 5 significant figures. Right? Non-zeros, now actually it's non-zeros and dashed zeros. Keep that in mind. Non-zeros and dashed zeros are significant. Zeros between, there are none. Zeros before, there are none. Zeros after the last non-zero. This is the first and the last non-zero. There's only one non-zero. Zeros after the last non-zero are significant if there's a decimal point. There's no decimal point, therefore these 3 zeros are not significant. Now, what I want you to keep in mind is that saying that these 3 zeros are not significant does not mean that you get rid of them. It does not change the number from 8,000 to 8. The number is still 8,000, but only the 8 is significant. All right, remember, saying that these zeros are not significant does not mean that they're not there. It does not change the number from 8,000 to 8. The number is still 8,000 with 1 significant figure. All right, here we go. Non-zeros and dashed zeros are significant. Significant, significant. Zeros between non-zeros and dashed zeros are significant. Zeros before, there aren't any. Zeros after the last non-zero or dashed zero. Here's the last non-zero, all right, L or dashed zero. This zero would be significant if there was a decimal point. There's no decimal point, so here you have 3 significant figures. Non-zeros and dashed zeros are significant. Zeros between, there are none. Zeros before, there are none. Zeros after the last non-zero, this is the first and the last non-zero, it's the only non-zero there, are significant if there's a decimal point. So that means that these 3 are significant because there is a decimal point. So here you have 4 significant figures. Non-zeros are significant. And remember, you're saying each of the rules quickly every time. Non-zeros and dash zeros are significant. Zeros between non-zeros are significant. There aren't any. Zeros before the first non-zero, F, here's the first non-zero. Zeros before are not significant. So this zero here is not significant. Zeros after the last non-zero are significant if there's a decimal point. There is a decimal point. We don't say where it has to be. Here's the last non-zero. Zeros after the last non-zero or dashed zero are significant if there's a decimal point. There's a decimal point, therefore these ones that are after are significant. Here you have, again, 4 significant figures. Let's do some more practice problems. Again, say each rule to yourself as you decide whether or not to circle each number. So here we go. Non-zeros and dashed zeros are significant. So that number is significant. Zeros between non-zeros, there are none. Zeros before, well, this is the first and the last non-zero. Zeros before the first non-zero, there are none. Here we go. Zeros after the last non-zero are significant if there's a decimal. There's no decimal. These 2 are not significant. This number has 1 significant figure. Now we're going to try to go a little bit faster. Non-zeros are significant. Non-zeros and dashed zeros are significant. Zeros between, there are none. Zeros before, there are none. Zeros after the last non-zero are significant if there's a decimal. There's no decimal. This is not significant. This number has 2 significant figures. Non-zeros are significant. This number has 1 significant figure. Non-zeros and dashed zeros are significant. Zeros between non-zeros and dashed zeros are significant. Zeros before the first non-zero, there are none. Zeros after are significant if there's a decimal. There's no decimal. This number has 3 significant figures. Non-zeros are significant. Zeros between, there are none. Zeros before, there are none. Zeros after the last non-zero. This is the first and last non-zero. Non-zeros after, zeros after the last non-zero are significant if there's a decimal. If there's a decimal, that zero is significant. So here we have 2 significant figures. What I think you should do now, pause the video and try the even ones, whether on a piece of paper or on the accompanying worksheet. Okay, so now check the work that you did and see if you got these right. Here we go. Non-zeros are significant. Zeros between, there are none. Zeros before, there are none. Zeros after the last non-zero are significant if there's a decimal. There's no decimal. These zeros are not significant. 1 significant figure here. Non-zeros and dashed zeros are significant. Zeros between non-zeros and dashed zeros are significant. Zeros before, there are none. Zeros after are significant if there's a decimal. 3 significant figures. Non-zeros are significant. 2 significant figures. Non-zeros are significant. Zeros between non-zeros are significant. Zeros before the first non-zero, there are none. Zeros after are significant if there's a decimal. There's no decimal. You have 4 significant figures here. Non-zeros are significant. Zeros between, there are none. Zeros before, there are none. Zeros after the last non-zero are significant if there's a decimal. 1, 2, 3. This has 4 significant figures. Let's try some more. Okay, let's try some more. And generally speaking, the even number that's straight across from the odd is similar, right, in some ways. All right, so here we go. Non-zeros are significant. Zeros between are significant. Zeros before, there are none. Zeros after the last non-zero are significant if there's a decimal. No decimal. 3 significant figures here. Non-zeros, zeros between, zeros before are not significant. Zeros after, there are none. 1 significant figure here. Non-zeros and dashed zeros, zeros between, zeros before, zeros after the last non-zero are significant if there's a decimal. There's a decimal, so those 2 zeros are significant. 1, 2, 3, 4, 5, 6 significant figures here. Non-zeros and dashed zeros, okay, there he is. Zeros between non-zeros and dashed zeros. So these 2 zeros that are between the non-zeros and dashed zeros, right, are significant. Zeros between are significant. Zeros before, there are none. Zeros after, only if there's a decimal. No decimal. 1, 2, 3, 4, 5, 6 significant figures here also. Non-zeros and dashed zeros are significant. Zeros between non-zeros or dashed zeros are significant. So these 2 are significant. Zeros before, there are none. Zeros after are only significant if there's a decimal. No decimal. You've got 4 significant figures here. Okay, so try the even-numbered problems. Pause the video, give them a try, and then I'll go over them and you can see whether or not you got this. Remember, say each rule to yourself. All right, here we go. And you're going to get faster, and you're not going to have to say the entire rule once you start getting used to it. Here we go. Non-zeros are significant. Zeros between non-zeros are significant. Zeros before, there are none. Zeros after are significant if there's a decimal. There's a decimal here, so these zeros are significant. 1, 2, 3, 4, 5, 6 significant figures. Non-zeros, zeros between, zeros before are not significant. Zeros after the last non-zero, this guy is significant because there's a decimal. All right, that's 3. Non-zeros, all right, zeros between non-zeros, zeros before, zeros after the last non-zero. Here's the first non-zero. Here's the last non-zero. Zeros after the last non-zero are significant if there's a decimal. This guy's significant. 1, 2, 3, 4, 5, 6, 7 significant figures there. Non-zeros and dashed zeros are significant. Zeros between non-zeros and dashed zeros are significant. Zeros before, there are none. Zeros after are significant if there's a decimal. There's no decimal. This guy is not significant. 1, 2, 3, 4 significant figures in that number. All right, now this is one example where this one and this one are not that similar. All right, generally speaking, whatever's in this column is very similar to what's in this column. All right, but here they're a little bit different. Okay, but here we go. Non-zeros are significant. Zeros between non-zeros are significant. Zeros before, there are none. Zeros after the last non-zero, right, this guy, is significant if there's a decimal. There's a decimal, so this guy is significant. 1, 2, 3, 4, 5 significant figures. All right, now you've got a whole bunch of problems to practice. All right, try them on your own. What I want to show you now is a different version of the same rules that we've already been applying. The rules for deciding which numbers are significant, version 2. Now, you should already have, you've been watching this video, you should already have in your mind that non-zeros and dash zeros are always significant. We got that. So really, all right, really, we're just looking at these two rules here. And again, these are the same rules that you've been applying, all right, just worded a little bit differently, all right? And here we go, okay? The first decision you make, you look, is there a decimal point or not? If there's no decimal point, this rule applies. If there is a decimal point, this rule applies, okay? So, if there is no decimal point, you go to the last non-zero or dashed zero. It and all the numbers to the left are significant, okay? Now, if there is a decimal point, you go to the first non-zero. It and all the numbers to the right are significant. All right, now, let's make this even shorter. All right, no decimal point, last, left, LL. If there's no decimal point, last and to the left. Okay? If there is a decimal point, go to the first and to the right. Okay? So now we're going to apply this version of the rules to those same problems. We're going to do the odd numbered problems. Okay? And you're going to see that this version is just the same as the other version. All right? This may be, you may like this version better. Whichever version you like better is fine. All right, now just keep in mind, all right, if there's no decimal, go to the last, that's the last non-zero or dashed zero, and it plus everything to the left is significant. Now, if there's a decimal, there will never be a dashed zero, okay? So, if there's a decimal, you go to the first non-zero, it and everything to the right is significant. All right, let's apply these quick versions of the rules, and here we go. All right? The first thing you decide, is there a decimal or not? All right? No decimal, last and to the left. One significant figure. All right? No decimal, the last, all right, non-zero or dash zero, it and to the left, all right, two significant figures. No decimal, all right, one significant figure. No decimal, all right, last and to the left. All right, three significant figures. There's a decimal, go to the first non-zero, it and everything to the right, so there are two significant figures. Okay? And remember, we're doing the odd ones only. Okay? You can practice the even ones on your own. All right, here we go. All right, decimal, all right, first and to the right, everything to the right. That's four significant figures. Decimal, the first non-zero, right? That's the first non-zero. It and everything to the right is significant. There's a decimal. Go to the first non-zero. It and everything to the right. 1, 2, 3, 4, 5, 6 significant figures. All right. No decimal. No decimal. Last and to the left. 1, 2, 3, 4, 5, 6. 6 significant figures. All right. No decimal. Go to the last, all right, non-zero or dash zero, it and everything to the left, all right? 1, 2, 3, 4 significant figures, all right? I'm not going to put up the answers to the even numbers because you already have the answers, but why don't you practice the even numbers now using this version of the rules, all right? No decimal, last, left. Decimal, first, right. Okay? Practice that. And then there's more practice problems, and then we'll go on to scientific notation. Okay, if you're using the worksheet, these numbers go straight down, the odd numbers. All right, and here we go. Let's try to do this quickly. All right. No decimal, last and to the left, one significant figure. All right, no decimal, last and to the left, three significant figures. All right, this one has a decimal, go to the first and to the right, so that's five significant figures. Okay, I think I'm going to stop circling at this point. We're going to try to go a little bit faster. All right, if it helps you to continue circling, please continue circling. All right, decimal, first and to the right, that's four significant figures. Decimal, first and to the right, that's five significant figures. 1, 2, 3, 4, 5. No decimal, last and to the left, that's 3. Decimal, first and to the right, that's 4. All right, no decimal, last and to the left, that's 3. No decimal, last and to the left, that's 4. All right, decimal, first and to the right, that's 1, 2, 3, 4, 5, 6 significant figures there. Okay, decimal, first and to the right, that's 2 significant figures. Decimal, first non-zero and to the right, that's 2 significant figures. All right, decimal, first and to the right, that's 4 significant figures. Decimal, first and to the right, that's 5 significant figures. No decimal, okay, last and to the left, 1, 2, 3, 4, 5, 6 significant figures. Okay, so do some more practice, okay? And what we're going to continue with is the relationship between significant figures and scientific notation, and then counted numbers and defined quantities. All right, and that'll be everything you need to know about significant figures. Now, what about numbers in scientific notation? Well, here's the rule that relates significant figures to scientific notation. When a number is written in scientific notation, all of the numbers in front of the multiplication sign, now that would be, here's the multiplication sign, so all these numbers, here's the multiplication sign, these two numbers, all right? Here's the multiplication sign, these three numbers. Now, all of the numbers in front of the multiplication sign, which are known as the mantissa or coefficient, right? The mantissa, the mantissa, the mantissa, right, are significant. So what we have here is the number 300 shown three different ways. Here's the number 300, 3 times 10 to the second power, 300 with one significant figure, 300 with two significant figures, 1, 2, and 300 with three significant figures, 1, 2, 3. Right? All of the numbers in front of the multiplication sign are significant. One significant figure, two significant figures, three significant figures. Now, the question becomes, how would you write the number 300 correctly in decimal form, indicating the correct number of significant figures for each of these examples? Now remember, this is the number 300, this is the number 300, and this is the number 300. But here the number 300 has one significant figure. So this is finished. One significant figure. Here, the number 300 has two significant figures. So you're going to need a dashed 0. All right, so that's showing 1, 2 significant figures. Here, the number 300 has three significant figures. So if you put a decimal there, that means that all of these are significant. 1, 2, 3. So in other words, you have to write the decimal number correctly to match the number of significant figures that the scientific notation is indicating. One significant figure, one significant figure. Two significant figures, two significant figures. Three significant figures, three significant figures. Let's try some examples. All right, let's figure out how many significant figures we have in each of these numbers in scientific notation, which is really easy. You just count the number of numbers in front of the multiplication sign and you're done. And then the trickier part, let's convert these numbers in scientific notation to decimal form with the correct number of significant figures indicated by how you write the decimal number. All right, so here we go. Here we have 2 significant figures. All right, here we have 1, 2, 3 significant figures. Here we have 4 significant figures. Here we have 1, 2, 3, 4, 5 significant figures. You see how easy it is. It's the number, all the numbers in front of the multiplication sign, which is known as the mantissa or coefficient, they're all significant. So here we have 3 significant figures. Here we have 3 significant figures. Here we have 3 significant figures. And here we have 4 significant figures. So now, when you write each of these numbers in decimal form, the way you write the decimal number must indicate the correct number of significant figures. So, to convert scientific notation to decimal, you're going to move the decimal point, the number of places indicated in the exponent. This is a positive exponent, so this is going to be a large number. We're going to move this decimal place 3 places to the right. All right, so we've got, if we start with 3, let's just say 3.5. I'm going to make that decimal really small because it's moving anyway. We've got 1, 2, 3. All right, so this number becomes 3,500. But to show only 2 significant figures, we're done. All right, we've got 2 significant figures there. Okay, how do you know that? You go through your list. Non-zeros are significant. Zeros between are significant. Zeros before, not significant. Zeros after the last non-zero are significant. If there's a decimal, there's no decimal, so these 2 zeros are not significant. But the number is still 3,500. All right, right here, 1, 2, 3. So again, the number is 3,500. But to indicate that all 3 of these numbers, 1, 2, 3, are significant, you remember you have to put a dash over that 0. You don't want to put a decimal point. That would indicate that this 0 is also significant. All right, so here we have 3 significant figures. And we'll double check all of these when we're finished. Here we have 4 significant figures. So again, you're moving the decimal place 3 places to the right. So you've got 4 significant figures. All right, put the decimal there, and that makes these 2 zeros significant. All right, here, all right, 3 places, 3,500. All right, put the decimal. So we've got 1, 2, 3 significant figures. That decimal makes these 3 zeros significant. Okay. Now here, 1.62 times 10 to the 0. 10 to the 0 is the number 1. So it's 1.62 times 1. So basically it's 1.62. Or you could say you are moving the decimal 0 places. Leave the decimal right where it is. Do not move the decimal. The decimal moves 0 places. 3 significant figures, 3 significant figures. All right, now here, this is a small number. A negative exponent is a small number. You're going to be moving that decimal point to the left. So 1 place to the left. 0.162. All 3 numbers are significant. They're all non-zeros. They're all significant. All right, here, 10 to the negative 2. 2 places to the left. 0.0162. All right, now, double check that you only have 1, 2, 3 significant figures. Non-zeros are significant. 1, 2, 3 non-zeros. Zeros between, there are none. Zeros before the first non-zero are not significant. This 0 is not significant, which matches 3 significant figures, 1, 2, 3 significant figures. Finally here, 2 places to the left, and there's a 0 on the end that must be significant. So, right here, 1, 6, 2, and a 0 on the end that must be significant. All right, let's double check that. All right, non-zeros are significant. 1, 2, 3. Zeros between, there are none. Zeros before, this 0 is not significant. Zeros before the first non-zero are not significant. Zeros after the last non-zero are significant. If there's a decimal, therefore this 0 is also significant. 1, 2, 3, 4 significant figures. 1, 2, 3, 4 significant figures. All right, now again, just double checking. Non-zeros, all right, and dashed zeros are significant. Zeros between, there are none. Zeros before, there are none. Zeros after the last non-zero are significant if there's a decimal. There's no decimal, so here we have 3 significant figures. Here we have 2. All right, here, non-zeros, zeros between, zeros before, zeros after the last non-zero, right? Here's the last non-zero, are significant if there's a decimal. There's a decimal, so these 2 are significant. All right? Non-zeros, zeros between, zeros before, zeros after the last non-zero, these are significant if there's a decimal. There's a decimal, they are significant. You've got 5 significant figures. We're just going to make sure that everything matches, okay? 3 significant figures here, all right? 3 significant figures here, all right? This is a different number. This is 1.62. This is 0.162. Non-zeros are significant. Zeros between, there are none. Zeros before are not significant, and there aren't any other zeros. So we've got 3 significant figures here and 4 significant figures there, okay? The number of significant figures in the decimal number must match the scientific notation. If you're taking this scientific notation here and writing it correctly as a decimal number, the number of significant figures must match. All right, now, what we're going to do is one more set where we go backwards in the other direction. Start with the decimal numbers, with the correct number of significant figures, and convert to scientific notation. All right, this is a little tricky, all right, so just hang in there. All right, starting with the decimal numbers, converting to scientific notation. All right, I would start by figuring out the correct number of significant figures in each decimal number. All right, so here we have 1 significant figure, all right? Non-zeros are significant, zeros between, zeros before, zeros after the last non-zero are significant if there's a decimal. There's a decimal, so therefore you've got 3 significant figures here. All right, non-zeros, zeros between, zeros before, zeros after the last non-zero, only if there's a decimal, so you've got 1 significant figure there. All right, here, non-zeros, zeros between, zeros before, zeros after the last non-zero are significant if there's a decimal. There is a decimal, so those 3 zeros are all significant. All right, let's convert those to scientific notation, and then we'll finish these guys down here. All right. So we've got, now you have to put in your imaginary decimal. There's an imaginary decimal here. There's an imaginary decimal here. All right. Now scientific notation, only 1 number in front of the decimal. This guy is fine. I don't have to move the decimal place, so the number of jumps is 0. So 6 times 10 to the 0. All right. We have 1 significant figure. 1 significant figure. All right, again, we do not have to move the decimal here. All right, so 6.00, 3 significant figures. We did not move the decimal point, so 10 to the 0 power. 3 significant figures, 3 significant figures. All right, now, we've got our imaginary decimal there, or the implied decimal. The implied decimal, this is the number 600. So we know that there's an implied decimal right there. All right. So we're going to move that decimal 1, 2 places. It's a big number. It's positive. It's going to be a positive exponent. All right. So 6.00, and we had to do 2 jumps. All right, to get this into correct scientific notation. So 2 jumps, 2nd power. All right. The exponent is 2. All right. Here. Again, 2 jumps, 1, 2, 6 point. We've got 4 significant figures. 3 of them are zeros. We did 2 jumps. There we go. Okay. Now, all of these are numbers less than 1. Right. So the exponents will be negative. All right. We've got 2 significant figures here. We've got 3 significant figures there. Remember, zeros before the first non-zero. Not significant, not significant, not significant, right? Zeros, this is the first non-zero. Zeros before the first non-zero, not significant, not significant. All right, so we've got 1, 2, 3 significant figures here. All right, 1, 2, 3 significant figures here. And 1, 2, 3, 4 significant figures there. So when we write these in scientific notation, we have to make sure that in the mantissa, the numbers in front of the multiplication sign, in this case, there's going to be 2 significant figures, in this case 3, in this case 3, in this case 4. All right, so now this guy is down here a little bit. All right, so we want to move the decimal place 1. So this is going to be 2.4 times 10 to the negative 1. How many significant figures? 2, 2. All right, move the decimal place. So there's only one number in front of the decimal. So this is 2.40 times 10, one jump. 3 significant figures, 1, 2, 3, 1, 2, 3. Right, one jump, it's negative because these numbers are less than 1. All right, these are small numbers. They get negative exponents. Big numbers, 1 or greater, get positive exponents or 0. All right, 0 or positive. All right, here, 1, 2 jumps. Right, so this is going to be 2.40 times 10 to the negative 2. All right, 1, 2, 3 significant figures, 1, 2, 3 significant figures, 1, 2 jumps, 2 jumps, small number, negative exponent. Okay, and finally, 1, 2, 3 jumps, okay, 2.400, right, 4 significant figures, 4 significant figures, 3 jumps, that's 10 to the negative 3. All right, so again, scientific notation is very easy in some aspects, some respects, because the numbers in the Mantissa have to all be significant. All right, so in this case, you had one significant number, so there's only one number here. This is the number 6, and this is also the number 6. But this number 6 has one significant figure. This number 6 has 3 significant figures. So it's 6 times 10 to the 0, right? 6 times 10 to the 0. But here we have one significant figure. Here we have 1, 2, 3 significant figures. Again, the decimal number and the scientific notation must match. If you're telling me that this is the decimal number that corresponds to this scientific notation, the number of significant figures must match in order to be exactly the same measurement. Now, the last thing we need to talk about, and this is really, really simple, would be counted numbers and definitions. All right, so what's the rule for significance when you are counting objects or defining measurements? Okay, so for counted numbers and definitions are also known as exact numbers. Infinite significance is implied. Again, infinity. All right, an infinite number of significant figures. Allow me to explain. Counted numbers. What are counted numbers? Well, if you're counting objects, then the number that you get is called a counted number. Now, if I have 6 M&Ms in my hand, and I actually counted them, 1, 2, 3, 4, 5, 6. Now, I mean, you can see the 6 M&Ms and you can corroborate that I counted those 6 M&Ms, or you trust me. All right, 1, 2, 3, 4, 5, 6. All right, there's no discussion about that. There are exactly 6 M&Ms in my hand. Well, not anymore, but in any case. So in other words, there were exactly 6 M&Ms in my hand. So this 6 has infinite significance. All right, it's the same as if you wrote the number 6.000 and an infinite number of zeros, which I'm not going to draw. All right, an infinite number of zeros following the 6. All right, these are counted objects or counted people. All right, in this case, people count as objects. What if there are 14 cars in the parking lot? All right, we have no doubt that somebody can count exactly 14 cars in the parking lot. All right, there are 14 cars in the parking lot. These cars were counted. All right, and we can imply or make the assumption that this 14 has infinite significance. 14.00000000000, etc. Now, the wording might tell you a little bit about whether or not the counted number has infinite significance. If you counted exactly 2,300 people, now that's not 2,299, not 2,301. If you counted exactly 2,300 people, you should put that decimal point there. If you counted every single person, maybe as the people walked into the stadium, right, you counted those people, and there are exactly 2,300 people in the stadium, well, you should have that decimal point there, and infinite significance is implied. What if you were to say there are about 2,300 people in the stadium? Well, if there's only about 2,300 people in the stadium, it might be 2,290, 2,296, 2,312, even 2,320 people, maybe. We don't know, because we only know that there are about 2,300 people in the stadium, so you definitely do not put a decimal point there, and we know that this number does not have infinite significance. If we counted exactly 302 ears of corn in the back of the pickup truck, right? Not 301, not 303, not 299, but we counted every ear of corn, and there are we counted exactly 302 ears of corn, all right? Infinite significance is implied, all right? It would be the same as if you wrote 302.00000 with infinite significance, all right? Judging by the way the statement is worded, all right, we can make some inferences about counted numbers and infinite significance. Now, if there are about 300 ears of corn in the truck, there might be 290, there might be 295, 297. This might be 330 ears of corn in the truck, all right? It says there are about 300 ears of corn, so we are not implying infinite significance in this case. All right, so again, numbers that you count, all right, there are 7 people in the room, infinite significance. All right, if you are telling people that it's an exact number that was counted, yes, you are implying infinite significance. Definitely put that decimal point there to show that these 2 zeros are absolutely correct. It's not 2,301, it's not 2,302, it is 2,300, 2,300 exactly. All right? If it's only about 2,300, well then you don't put the decimal there because we're not sure about these 2 zeros. All right? These 2 zeros are not significant. Now that doesn't mean you get rid of them. That doesn't mean there's only 23 people in the stadium. There's still 2,000-ish people in the stadium, but, all right, these 2 zeros are not significant. Maybe there's 2,308 people in the stadium. All right, so counted numbers, all right, not this one, all right, not this one. All right, but the other 4 examples on this page, counted numbers, have infinite significance. This becomes important when you start adding, subtracting, multiplying, and dividing significant figures in the upcoming videos. And finally, definitions like counted numbers also have infinite significance. 1 hour, that number 1, has infinite significance. It's 1.00000000. I could go on all night. This 60 also has infinite significance. This is a definition. 1 hour is defined as exactly 60 minutes, 60.000000. Remember, what we're talking about here for both counted numbers and definitions is an infinite number of significant figures. And the reason this is going to be important is in later videos where we are adding, subtracting, multiplying, or dividing with significant figures, the infinite significance will be important when you use counted numbers and definitions. 1 inch was defined early in the 19th century by both the United States and Great Britain and several other countries as precisely 2.540 centimeters. So again, this definition, 1 inch, the number 1, and the number 2.540, both have infinite significance. 1 centimeter is defined as exactly 10 millimeters. This 1 and this 10 have infinite significance. It might as well be written 1.000000, go on forever, equals 10.000000, go on forever. Infinite number of significant figures, infinite number of significant figures. 1 dozen, right? This 1, infinite significance because it is defined as exactly 12 objects. Whatever those objects are, doesn't matter. This 1 has infinite significance. This 12 has infinite significance. Okay, so you're going to want to practice, practice, practice. Significant figures are really easy if you practice, practice, practice. And again, if you want to understand why significant figures are important to engineers, doctors, pharmacists, architects, all right, people in careers where people's lives are at stake, all right, then watch the video right before this one that describes why significant figures are important.